Hello everyone, I'm Nirupam and I'm welcoming all of you once again to Saurav's classes. So I'll be discussing problems in this lecture on the growth theory, and basically I'll be discussing the problems given at the end of chapter 1 of the book titled Advanced Macroeconomics, third edition by David Rummer. So the publisher is McGraw-Hill Irwin, and I'll be following the structure. We'll be basically discussing the problems. I'll be writing down the problems on the whiteboard, and then I'll be discussing the solution to the problems, and in a way that will also help you to understand the nuances of how the things actually work in the practical sense. So this is the problem 3 of the end of the chapter section that I'll be discussing. So let us see what is the problem all about. So the problem is that we will be discussing. So this discussion is basically about the the investment part. So basically it is talking about the level. So how we'll see in this problem that how the level of the capital per unit of effective labor actually varies when we play around with the different parameters of the solo growth model. So there is a relationship that is at the optimum, and that is at the optimum if we are let's say if the production function, that is, this is a production function in this intrinsic form where small k is nothing but the capital available per unit of effective labor. So once we do that, and we are saving proportion S of this product, that is this is a savings rate in the economy. So this we are saving for the capital, for investing in the capital, which is one of the factors of production, and at the optimum this savings or total savings in the economy should be equaling the break-even investment. So break-even investment is investment that we need to make so as to keep the per unit capital, so as to keep the level of capital per unit of effective labor from falling. So the break-even investment is given by this, that is n plus g plus del of n plus g plus del of k. Okay, so k is the this is the level of the capital per unit of effective labor in the economy, and this is the savings in the economy for investment for forming capital. So at the optimum, that is at the margin, it should be at least equal to the break-even level of investment, because if the investment falls below this break-even level of investment, then effectively what happens is that my capital per unit of effective labor keeps falling. So I will be only operating at that point where this is where it is just replenishing the break-even level of capital investment required to keep the small k from falling. So now if we put it, let's say, graphically, so where we are plotting k on the horizontal axis, and all the we are plotting k on the horizontal axis, and all your other definitions, that is this s of fk and n plus g plus del of k on the vertical axis. Okay, so we see that this is, so in the solo growth model, n is nothing but the rate of growth of capital, g is nothing but the rate of growth of knowledge accumulation. So n plus g stands for the rate of growth of effective labor, and delta is nothing but the depreciation of the capital. So this is something which is taken as fixed or given in an economy under the solo growth model. So for this it will be a straight line, the graph of this break-even investment with a straight line with a slope n plus g plus delta. So this is the break-even investment line, that is n plus g plus delta of k. Now f of k, that is the intensive form of the production function, which is a function which is again itself a function of the capital per unit of effective labor, and a proportion of s which is being saved for investment will be depicted by this graph. so which is nothing but so the point at which this graph, that is S of f of k, intersects the break-even investment line will give you the point of optimal capital per unit of effective labor. Now let us assume, so these are the basic parameters which you can find are as follows, that is S, N, G, delta, okay. So these are the main parameters, exogenous parameters which are given, and let us see how the optimal level of small k changes as we keep on changing the values of these parameters. So the first part of the problem is this, that is the rate of depreciation is falling. That means delta is now falling. So when the delta falls, that means this line, that is the break-even investment line, will now become even more flatter compared to the original line. So now let's say it is becoming flatter, okay. So it has now become flatter. So n plus g plus delta nu, because the new depreciation rate is lower than the old depreciation rate, and hence the S of fk curve is now intersecting the flatter break-even investment line at a higher level of optimal k, which is given now by k star nu. So what happens when the rate of depreciation is falling? That means the minimum level of investment which you require to keep the small k from falling actually falls. So hence now you can even keep on investing more till again you reach the point where the investment for capital is equal to the break-even investment, which is at a higher level of small k. Okay. Now let us see what happens when we are, so this is a part of the problem. The part of the problem is that what happens when the rate of technological progress rises. Now the rate of technological progress is nothing but given by the rate of knowledge accumulation, which is nothing but given by this rate g. Now when this g is rising, that means effectively my n plus g plus b is rising. So hence the new break-even investment line will be even more steeper than the original break-even investment line. So now let us see what happens when this break-even investment line becomes more steeper. So this is now become more steeper, where the new g is greater than the old g, whereas n and delta remains unchanged, and hence now it is intersecting the investment line, that is S of fk line, at a much lower level of capital, which is now given by k prime nu. Okay. So now you require even higher level of break-even investment to keep the k from falling, and hence it now intersects the investment curve at a much lower level of k prime. This is, so the logic is this. So if you see that f of k is nothing but the production function, and the first derivative with respect to k is nothing but the marginal product of capital per unit of effective labor. So as you keep on increasing k, this marginal product keeps on falling, but at lower levels of k this is quite high. Now which is so S of fk is nothing but the what is the marginal increment in so what is the marginal increment in the investment that is happening following the marginal change in k. So as we see that there is a higher level of higher level of break-even investment required, so it is this implies that we can match up to this higher level of break-even investment only if the marginal product of the small k is higher, which can only happen if you are operating at lower levels of small k. So when this break-even investment becomes higher following an increase in the rate of technological progress, or for that matter for any of the parameters, that is either n or g, then the optimal level of capital at which we will be reaching the break-even investment level in small k will be much lower, and that's what we are finding here. Now the third part of the problem. So the third part of the problem is this. Now we are assuming that f of k is that of a Cobb-Douglas production function, and the capital share, that is alpha, is rising. So what happens when this is taking place. So right at the outset, it will be very difficult to say about the impact of increase in the capital share, that is alpha, when the intensive production function assumes the form of a Cobb-Douglas production function, that is K of alpha. So what we will be doing, basically we will be differentiating, that means we will be differentiating the investment which we are making, that is S of f of k with respect to alpha, that is we will be doing this, that is del of S of fk del of a alpha, which is nothing but del of S of k alpha del of alpha. So once we do that, what we find, so S is the constant, so it will stay outside, so it is again del of k of alpha del of alpha, which is nothing but S into alpha k to the alpha minus 1 del k del alpha. So we can write again this as S alpha by k, so k to the power alpha, so del k del alpha, so again S of k to the power alpha, so again we can write del k, okay, del k by k del alpha by alpha, so which can be written then as S of k of alpha, okay, so S of k of alpha log of k, okay, so S of k of alpha log of k. Now we can see that what will be the impact on the investment, on the level of the investment following the change in the alpha, where alpha is rising. So this can only be said following the sign. So we know here that S is a positive number, and if alpha will always rise line between 0 and 1, that means alpha is also positive, and hence k to the power alpha, so it will depend. So now if k is greater than 1, log of k will be greater than 0, and hence del k of del sf of k by del alpha will be rising. Now if k is less than 1, then log of k will be less than 0, and hence del s of fk by del alpha will be falling, that means it is less than 0. And if k is equal to 1, log of k will be equal to 0, and hence there will be no change. That means s of f of k, s of fk will not follow any change following the change any change in alpha. So now if we assume, so now we will be showing one of these situations whereby k is greater than 1, that means del of k is greater than 0, and hence del of s of fk by del alpha will be greater than 0. That means s of fk is rising when alpha is also rising. So we will show this thing now graphically. So in addition to this, the question which is also coming to mind is this, that what will happen to the level of the optimal k, that is small k, following an increase in alpha. So this will actually depend on the relative magnitude. So it will depend on the relative magnitude of S and n plus g plus delta. Now if S is greater than this growth, that is n plus g plus delta, then it is going to happen that following an increase in alpha, there will also be an increase in the optimal k, which is what we'll be showing here. That is plotting k on the horizontal axis, and this is the break-even investment line, that is n plus g plus delta of k. This is the initial investment line, that is S of f of k. And now following change in alpha, that is rise in alpha, there is also now an increase in S of f of k, that is okay. So S of f k okay. So now what is happening? Initially the capital K was this at this level, K star nu, K star. Now following the increase in alpha and given the fact that S is greater than n plus j plus d, so the rise will be such that there will be an increase in K star. So it will change from now K star to K star nu, where K star nu is greater than K star. Okay. Now the fourth part of the problem. So the fourth part of the problem is this, that is now the workers are putting more effort. Okay. So compared to the original situation, the workers are putting more effort, so that output per unit of effective labor for a given value of small k, that is capital per unit of effective labor, is actually rising. So let us see what happens in this situation graphically. Okay. So to do this, what we will do initially, so initially we will be considering the intensive production function, that is production function is intensive form, that is f of small k. So we will be modifying this intensive form of production function by introducing a constant b, where b is a positive number, that is b is greater than 0. Now when let us assume that the worker effort is increasing so that the output per unit of labor for a given value of small k, that is capital per unit of effective labor, the output is rising. That means here we will now be assuming that b which is positive is also rising, and hence this b of f of k will also be rising. So b here is actually denoting a work level of the worker effort. So when the worker effort rises, b also rises, and hence b of f of k also rises. So we know that the investment is nothing but a function of fk, and in this modified f of k small k and this modified intensive function form of production function, it will be nothing but s of b of fk. So when b is rising, that means this is also rising, and hence there will be an outward shift of the investment line in the graph. So let's see how this happens. So again on the horizontal axis we are plotting k, and on the vertical axis we are plotting s of f of k modified as s of b of k, as well as the break-even investment, which is n plus g plus delta of k. Now when we do that, so this is the break-even investment line, which is n plus g plus delta of k. This is the initial investment curve, which is nothing but s of b of f of k. Now following an increase in b, the investment line now shifts outward like this, and such that it now becomes s of b of nu of f of k. So initially the optimal level of small k was k star. Now following an increase in worker effort and hence rise in b, the investment line shifts outward and intersects the investment curve, shifts outward and intersects the break-even investment line at a new level of small k, which is given by k star nu. Okay. So this is the function which so this is what happens. So if there is an increase in worker effort, then the investment will also rise, the per unit investment will also rise as for a fixed proportion setting, and it will now lead to much higher level of capital per unit of effective labor in the economy, given that the break-even investment level of investment remains unchanged. Okay. So so this was the discussion regarding the impact of the changes in the parameters of this investment relation, that is s of f equal to n plus g plus del of k, and how change in each of these parameters can affect the optimal level of small k, that is a capital per unit of effective labor in the economy. So thank you for listening to this lecture and hope you have enjoyed the lecture. So thank you once again.